Hello, today I'll explain my role in the project, which is using the LSM60S3 sensor to monitor vibration in a Formula One system. The LSM60S3 is a motion sensor that includes both accelerometer and gyroscope, but in our project we mainly use the accelerometer to measure vibration. The sensor reads acceleration in three axes, X, Y, and Z, and from these values we can understand how much the system is vibrating. In a Formula One car, vibration is very important because executive vibration can affect performance, damage components, or indicate a mechanical issue. So instead of just reading raw numbers, we designed a system to classify vibration into three clear stats: good, bad, and warning, which makes it easier to monitor the system in real time. Now I'll explain the code and how the system works as a whole. At the beginning, the code initialized the LSM60S3 sensor using I2C communication, and also initialized the SD card module. The SD card is used to store all the vibration data so we can analyze it later after the run, just like a data logging system in Formula One. After initialization, the system performs a calibration step. During calibration, the system must stay still, and it takes multiple readings from the sensor to calculate an average value called the baseline. This baseline represents normal conditions with no vibration, and it's very important because all future measurements are compared against it. Once the system starts running, it continuously reads acceleration data from the sensor. The code takes the X, Y, and Z values and combines them into a single value using the magnitude equation. This gives us the total acceleration acting on the system. Then, the code subtracts the baseline from this value to isolate only the vibration component. After that, it calculates something called RMS, which stands for root mean square. RMS is used to give a more stable and accurate measurement of vibration strength instead of relying on a single noisy reading. To make the system even more stable, the code applies smoothing using a weighted average. This reduces sudden spikes and makes the output more realistic and easier to analyze. After calculating the vibration level, the system compares it with a predefined threshold. If the vibration is low, the system outputs good. If it's moderate, it outputs bad. And if it's high, it outputs warning, which indicates a potentially dangerous condition. However, the system doesn't immediately change the stats. It uses a stability filter, which means the same result must appear multiple times before the stats is updated. This prevents false alarms caused by noise or sudden spikes. Finally, every reading is saved into the SD card in an Excel file. This allows us to review the data later, similar to how Formula One teams analyze telemetry after a race. And now I will show you some videos demonstrating the three different sensor stats: good, bad, and warning.
This part will be covering simulating Formula One suspension displacement with the rotary potentiometer. In Formula One, monitoring suspension movement is essential for maximizing grip, stability, and overall performance. Engineers rely on precise displacement data to understand how the car behaves under different conditions. In this project, I created a simple system that simulates suspension displacement using a single rotary potentiometer and an Arduino Uno. A rotary potentiometer is a variable resistor that changes its output voltage depending on its angle of rotation. In a Formula One car, sensor would measure actual suspension travel. However, in this project, the potentiometer is manually rotated to simulate the movement of a suspension. This allows to replicate how displacement data would be generated without needing a physical suspension system. The setup is straightforward. A connected rotary potentiometer to an Arduino Uno. The potentiometer has 3 pins, one connected to 5 volts, one connected to ground, and one connected to the pin A0 of the Arduino. As the knob is rotated, the voltage at the analog pin changes, and the Arduino reads this as a value between 0 to 1023. The code used in Arduino IDE is to read and process the data. First, I define the analog pin and create variables to store the potentiometer value and the calculated displacement. Then include calibration values, a minimum and a maximum reading, which represent the simulated limits of a suspension travel to be more accurate. Inside the main loop, the Arduino reads the analog value from the potentiometer. The value is mapped to a displacement range, which is the usual displacement of a suspension from 0 to 15 millimeters. This step converts the change in voltage into a meaningful physical measurement, even though the movement is being simulated manually. Finally, the displacement value is printed to the serial monitor for real-time observation and data collection. The calibration ensures that the system provides consistent and realistic values by setting minimum and maximum readings. The full rotation of the potentiometer corresponds to the full range of simulated suspension displacement. The output data from the serial monitor can be logged and transferred into Excel to generate graphs, allowing visual analysis of how the system's suspension moves over time. In conclusion, the project demonstrates how suspension displacement measurement works at a fundamental level. Although it does not use a real suspension system, it accurately simulates the data acquisition process used in motorsports. This provides a clear and practical understanding of how sensors and microcontrollers can be used to monitor vehicle dynamics.
In this project, I developed a tire temperature monitoring system using an infrared sensor inspired by its applications in Formula 1. In Formula 1, tire temperature is extremely important because it directly affects grip, performance and safety. Teams constantly monitor tire temperature to make strategic decisions during a race. So the aim of my project was to simulate a simplified version of the system using an infrared temperature sensor. For the hardware, I use an MLX90614 infrared temperature sensor connected to an Arduino. This sensor has 4 main connections: VCC, GND, SDA, and CSL. A VCC is connected to a 5 volts, GND goes to ground, SDA is connected to analog pin A4, and CSL is connected to analog pin A5. These connections allows the sensor to communicate with the Arduino using I2C communications. The sensor is ideal for this application because it measures temperature without direct contact, which is important for something like a moving tire. I also interrogated an SD card model to log the temperature data so readings can be stored and analyzed later. In terms of software, I wrote a program that reads the temperature from the sensor. The raw temperature value is then calibrated using a scale and offset to improve accuracy. After that, the system classifies the temperature into 3 conditions: good, warnings, or bad, depends on the range. To test and calibrate the system, I used a thermometer as a reference and a hairdryer to gradually increase the temperature. This allows me to compare real-world values with the sensor reading and adjust the calibration accordingly. As you can see from the graph, the temperature readings increases steadily, showing that the sensor responds consistently to heat changes. This demonstrates that the system is working reliably. Finally, the data is printed to the serial monitor and also saved onto the SD card, making it useful for further analysis, similar to how real Formula One teams collect and analyze tile data. Overall, this project demonstrated how infrared sensor can be applied in a real-world motorsport context, and how data logging and calibration are important for building accurate monitoring systems.
For this part, I will be talking about brake disc temperature monitoring. F1 brake discs operate at very high temperatures, often reaching 400 to 600 degrees. Monitoring these temperatures is crucial to ensure performance, safety, and prevent brake failure. This project focuses on developing an embedded system to monitor the brake disc temperature in real life. The sensor that is used for this project is a K-type thermocouple connected to a MAX 6675 module. The thermocouple is suitable for high temperatures, while the MAX 6675 converts the small analog voltage into a digital signal that can be read by the Arduino. This shows how the thermocouple is connected to the MAX 6675 module, which is then connected to the Arduino. An SD shield with a built-in RTC is used to log temperature data along with real time and date. And here is the code that is used. This code reads the temperature from the thermocouple and classifies it into the three conditions: warning, good, and bad. It also logs the data onto an SD card. This code is user customizable, allowing the user to set the temperature thresholds. This is important for testing because lab conditions cannot reach real brake disc temperatures. Here it shows the output of the system. The temperature is displayed along with the condition. As the temperature increases, the system transitions between warning, good, and bad states. Two types of testing were done for this system. The first one is calibration testing. It was done by using a lab hot plate and a calibrated thermocouple. Later on, the code temperature was compared with the lab calibrated thermocouple temperature at different set points. The graph shows that both values follow a similar trend, indicating good accuracy. For the second test, SD logging was used. The temperature data was logged over time using an SD card that is on the SD shield. The readings were recorded every 1 minute and then plotted in Excel. The graph shows how temperature changes over time and confirms that the system can reliably log data. The final system setup, which combines all of the previous sensors mentioned. This is the final code that was made by combining all of the previously mentioned sensors. Output of the integrated code. It shows each parameter of brake temperature, tire temperature, vibration, and suspension displacement.